Okay, so I hope you watched the guy in the orange hat where he's talking about piles of X bars, piles of sample means. And this is a really important concept in order to go do much more with statistics. And that's actually where statistics starts getting cool, I think. What's going on here? So we did that work with the normal distribution last week. And now what's happening is they're telling us that the average for these potatoes, the average weight for these potatoes are 8 ounces and the standard deviation is 1.2. What if we get a sample of 4 potatoes? They want us to find the probability that the average weight, the mean weight for those 4 potatoes is less than 10 ounces. So if we were just doing this pretending it was a single potato, we'd say the mean was 8 ounces, the standard deviation is 1.2, so if I add 3 lines on both sides, remember I'm going to add 1.2, right? That's the mean, or the standard deviation. That'd be 9.2. That'd be 10.4, and that would be 11.6. Then if I subtract 1.2, that would be 6.8, and 5.6 and 4.4. So that's telling me that practically all the potatoes in this guy's gardens will fall between 4.4 ounces and 11.6 ounces. What did I just do here? Okay, so then they're asking me what's the probability that the mean weight would be less than 10 ounces? Well, let's see. Let's go to a highlighter, I think. Less than 10 ounces. Well, I don't see 10 ounces. 10 ounces isn't one of those nice 68, 95, 99.7 rule numbers. So it looks like we got to go use that David Lane applet. And less than 10 ounces means we're looking for that area. So the area below. So I put those numbers, those values so for the single potato, I put those values into the David Lane applet, mean of 8, right, 8 ounces, standard deviation is 1.2, and then we said below 10, well, that tells me 95%, a little bit better than 95% of the potatoes will weigh less than 10 ounces. That's one potato. Now this is asking for 4 potatoes. So what changes, and this is I don't know, he talked about it quickly in the video, but what changes is your standard deviation, because samples vary less than individuals. So the way what the central limit theorem tells us, it says to find the standard deviation for all those sample means, notice that little notation I'm using, you take the old standard deviation for the population and you divide it by the square root of the sample size. So in this case for A, I'm going to take the old standard deviation of 1.2 and I'm going to divide it by the square root of 4 because I got 4 potatoes. Well, if I grab a calculator, or maybe you know the square root of 4 is 2, and 1.2 divided by 2 is 0.6. So that's the standard deviation for the sampling distribution. Now, you don't have to do this part, but let's see if I can do this. Let's see what I want. Can I erase this stuff? No, I can't. So what's going to happen, that changes the distribution, and it's going to shrink it up. I know what I do. I'll do this with David Lane, and that'll generate the well-labeled sketch for me. So I'm going to go back out to the David Lane applet. I'm going to substitute in 8. Here. I'm going to substitute in 8 and this new standard deviation, because I know that samples vary less than individuals, and that'll give me a different probability. So what I've done here is, here's the old one that I just calculated with 1 potato, that the probability of 95% of the potatoes weighed less than 10. With a sample now, I noticed I changed the standard deviation to reflect the smaller standard deviation because of the sample size of 4, and I still see same mean, new standard deviation was still below 10, and see how I've got almost all 99.96% of the potatoes would the average. So 99 points, I better say this correctly, 99.96% of the potato, the average, no, see I messed up again. It's 99.96% of the samples of size 4. In other words, we went out, took out 4 potatoes, weighed them, find the average, put them back in, mix them all up, take out 4 more potatoes, weigh them, average them, all those samples, and we did this an infinite number of times, and then we wouldn't do this, but that's what theory says we could do, and we'd find that 99, almost 100% of the samples would have an average weight of 10, is this number here. So a much higher percentage than an individual potato. Okay. So what happened? So then, here, let me stop this for a minute. Okay, so now for part B, it says, what if you've got a sample of 20 potatoes? Well, what changes there? Well, I know I'm going to take 1.2 and divide it by the square root of 20. And I did that earlier here. Let me see if I can find it. So I know the square root of 20 is about 4.47. Remember, you hit the square root x button on your calculator. So take 20, hit the square root of x. And then 1.2 divided by 4.4, I got 0.268, and I'm rounding. So that's the new standard deviation. Notice it's smaller than with a sample size of 4. A sample size of 20 gave me a much smaller standard deviation. There's going to be less variation in how all those sample averages, sample means group around the population mean of 8. So let's go ahead and use David Lane to figure out that probability. So this one, as you can see, that probability says it's 1. It's very unlikely, I mean almost impossible, to get a sample of 20 potatoes and have their average be more than 10, because the probability that they're less than 10 is 100%, all right? So that's why larger sample sizes really lock things up, and you can make some good judgments about that. Provided you get a random sample, that's really important to get a random sample. Okay. Let's see, I guess that's that. So I think we've done that. Now we just have part C says, suppose Carl's bags, so groups of 6. Now we're having only 6 potatoes, and we're going to find what percentage of bags there'll be a half an ounce. So the average will be half an ounce less than 8 and half an ounce more than 8. So let's see what changes with this. Let's see. So what changes, the central limit theorem says those averages of size 6 will have a standard deviation of 1.2 over the square root of 6. So on my calculator, I just went ahead. I was really being lazy. Not lazy, I just did it all in one swoop. I went 1.2 divided by the square root of 6, and that got me 0. Let's see, what did it give me? It gave me 0.48989, blah, blah, blah. So I rounded to 0.49, I believe. Okay, so average of 8, new standard deviation of 0.49. Let's find that probability of getting a group of 6 potatoes that have a mean weight between 7.5 and 8.5 ounces. Notice we're talking about samples here. We're talking about a mean, not an individual. So, but we can use David Lane just the same. So notice, so this is telling me 69%, just a little bit better than 68%, right? And we can kind of see this just a little bit. Remember, those are the 68% cutoffs for the 68, 95, 99.7 rule. Still holds for, even though we're talking about samples, but it's a little bit more than that. So that's that probability. So what's the chance of getting something outside of that or less than that? Well, let's see. If this is about 69%, we'll do some rounding here. So that's 31% outside of that. So isn't that 15.5% below and 15.5% above? So there's a 15.5% chance of getting a sample of 6 potatoes that have an average less than 7.5 ounces, and there's a 15.5% chance of having, that's 15.5 is what that should read. A percent chance of getting a sample of 6 potatoes that have an average of more than 8.5. Okay, I'm getting that from those. Okay. Now, how about this last one? It says, let's see, what does it say? It says, suppose you buy a bag of Carl's potatoes at the farmer's market, and each bag contains 6 potatoes, and your bag weighs 42 ounces. Would you feel cheated? Well, what's the average weight? If I have, so what's the mean weight for the sample? Well, I've got 42 ounces for a total, and I've got 6, so I have all 6 potatoes added up to 42 ounces. So we'll divide it by 6 ounces. So that means on average, each potato weighs 7 ounces. Now, if the mean is 8, does that seem like we're getting ripped off? Maybe, but you got to, because samples vary a lot, you've got to do a little bit of work with this. And what we're going to do is we've already got the standard deviation. Let's see, we know the mean for this population is 8. We have the standard deviation for samples of 6 is, what was that, 0.49 we said earlier? Let's go throw this into David Lane. So what we're going to do, here's a little quick sketch, and then we'll see, make sure it's what we're seeing in the David Lane applet. 8 is the mean, 7 is the average weight for this bag of potatoes we bought, and we're looking for that area. We're looking for that probability. So I put those numbers into the David Lane applet, below 7. So there's only a 2% chance, a 2.1% chance of getting a bag of 6 potatoes and having the average weight of those potatoes only be 7 ounces. So usually what we say, more than 2, remember how we did when 2 standard deviations was an outlier? See how that's below, remember that's 2 standard deviations below the mean, and it's actually smaller than that. Or the other way to think about it is if it's less than, if the chance of something happens is less than 5%, then it's also unusual. And sure enough, that's less than 5%, or this is more than 2 standard deviations. So yeah, it's not likely to get a bag of 6 potatoes with that low an average weight if 8 ounces is the true mean weight. So yeah, something's up. Either it's a bad sample, maybe it wasn't a random sample, which is a possibility. Am I going to lose a lot of money if I go accuse the guy that he's ripping me off? Probably not, but this is we can extend this into more complicated situations. Okay, so that's how that works. Okay, so we've left potatoes behind. Now we're about catching fish, bass. And they're telling me that the bass in this lake are normally distributed. The weights are normally distributed, which is good. That lets me use all these tricks. And then the mean is 2.2. So the mean weight for these fish are 2.2 pounds with a standard deviation for the population of 0.7 pounds. And we're looking to start with a sample of size 3. Pretty small sample, but we'll keep it start easy here. So we got to figure out the new standard deviation for all those samples, those piles of X bars for size 3, so 3 fish. So we're going to take that old standard deviation divided by the square root of 3. So I'm just going to key that right into my calculator, that divided by square root 3, all right? And I'm getting on my calculator about 0.4. I mean, there's more decimal places, but it rounds to this, so that's a pretty nice number to use. So that's my new standard deviation. So how likely is it to get a fish, or get a sample of 3 fish, then the average weight's only 1 pound? That's what we're looking for. So is that unusual? I don't know. Let's make a little sketch of this, and then we're going to go use David Lane to calculate. You knew I was going to do that. Well, let's go 3 lines below, because I don't really care about above it. Because I'm talking about one pound fish. Now, if the standard deviation is 0.2, let's see, isn't this going to be 1.8? I said if the standard deviation is 0.2. If the standard deviation is 0.4, I'm going to subtract 0.4 from 2.2, I think I get 1.8. I'm going to subtract 0.4 again. That's giving me 1.4. And I'm going to subtract 0.4 again, and I'm getting 1. So lo and behold, that actually is in one of those nice 68, 95, 99.7 rule numbers. And if you go back and look at that normal curve sheet that we worked on last week, you'll see that 1, 0. So we're 3 standard deviations below the mean. That means 99.7% of the samples of size 3 have weights between 1 and whatever the upper number is. And outside of that, if you look at that paper, you'll see that it's 0.15%. So a pretty small likelihood, that's a pretty small chance of getting a sample of 3 fish and weighing that little if 2.2 is the real average. Now, you don't want to have to do this every time. I'd really like you to be able to use that David Lane applet also. So let's go set some stuff up, and I'll show you what that comes up with. Okay, so I went out to the David Lane applet, and I substitute in the new mean and the new standard deviation. And for below 1, well, let's see. Remember how we said it was 0.15%? Well, if we make this a percentage, isn't that 0.13 if we do some rounding? So it's very close to the 68, 95, 99.7 rule of thumb. And see, that's why it is just a rule of thumb. That's approximately what it is. But that's a pretty good approximation. So again, it's unusual because that's less than 5%, or that's 3 standard deviations below the mean. So that's quite a ways below that. So we would be questioning the 2.2 average. Either we had a bad sample, or we would be questioning the 2.2 average. Let's go on and do a little more. Okay, so for this next problem, it says I'm catching 3 bass again. So that means I'm still using that same new probability, right? The 0.7 divided by the square root of 3. They want us to find the probability that the mean weight of those 3 fish is more than 3 pounds. So we're looking for if the lake's average, if the population mean 2.2 pounds still the middle, we'll assume it is. And if we're testing to see what's the average of getting the probability of getting 3 fish whose average weight is 3 pounds or more. So we'll put all of this into that David Lane calculator. So what am I seeing? I'm seeing, so it looks like the error. It's just barely, I guess it's exactly 3 standard deviations, or 2 standard deviations above, isn't it? So that the 68, 95, 99.7 rule would tell us, oh, if there's 95% in the middle, there's 5% outside that, and 2.5% below, 2.5% above. Notice that's 2.28%. Again, pretty close to what the approximation was. Okay, so is that unusual? Yeah, it's less than 5%. We could say it's probably unlikely to happen if the true mean is 2.2. So then for part C, notice we're still talking about random groups of 3 fish. We want to know what's the probability they'll weigh between 2.2 or 2 pounds and 2.4 pounds. It looks like 0.2 pounds either side of the mean, right? So again, we'll just go use that David Lane, and I hope you see that this is, well, let me make a little quick sketch. So 2.2 in the middle, then we're going to go 2 to 2.4, and we're looking for that area right there. So let's go throw this into that David Lane calculator and see what we get. So they threw it in for us, and certainly less than, we know that would have 68% of the distribution there, of all the samples would fall in between that amount. And so this should be less than 68%, and sure enough it is. So 38.29%, if you want to write as a percentage. Okay, nothing earth-shattering there. So how about this next one? Here, let me do some more deleting here. So what's different for this one is, let's see, we have a mean of 2.2 pounds again. And the population standard deviation again is 0.7, but because now we're dealing with a sample of 6 fish, won't that be 0.7 divided by the square root of 6? And let's see, I did that someplace else, right here, and I got about 0.286, I rounded to. And then I've got 6 fish that have a weight of 16.2. So let's find the mean for those fish. How much is on average those 6 fish weigh? So 16.2 divided by the square root of 6, right? So I did that earlier and I got 2.7 pounds. So the average for those 6 fish is 2.7 pounds, which is more than 2.2. Is it far enough away to say that it's something going on, or just, it isn't an unusual amount? Well, let's make a little sketch so I know what I'm looking for. 2.2 in the middle, 2.7 above, and I want that area. That's my probability, right? So it'll be above. So let's go use David Lane's calculator again and figure this out. So then I'm looking, so here's the result. I see that an average of 2.7 here. Let me get a marker going here. 2.7 is less than 2 standard deviations above the mean. So maybe, the probability is less than 5%. So maybe you could brag. It's not really unusual because you're within 2 standard deviations, but are you a great fisherman because you're able to beat the average? You could make the case for it. You could also, somebody might counter and say, well, maybe you were just lucky. Yeah. But that's what we do. We'll go with this later on. Well, I don't know if we're going to have time to do that this year, but we want to show that it's statistically significant. And in this case, you might not be able to do that. Well, the probability is less than 5%, so we might say yes, it is different than 2.2. It's kind of the jury's out still on this, is how I would come up with that. Okay, so that is that problem. Okay, so now for this one, we're talking about 2 different groups of people. Oh, wow, look at the date. I just noticed 2009, 2010. He wrote this textbook in 2014, so that's why he's using such old data. It'll work. It'll get us. It's the same. The math hasn't changed. So we've got 13 men. They aren't telling us whether it's normally distributed, but heights and weights usually are. Things that occur in nature usually are normally distributed, symmetric. And so first off, we're talking about U.S. men. So we've got 2 different distributions going on here, right? We got U.S. men height, U.S. men standard deviation, U.S. men weight and in their standard deviation, and for NBA players. And where we're gonna go with this is we're gonna ask, are they 2 different populations? So let's do some work here. So I know for A, I know n equals 13. I know the mean height is 69.3. And the standard deviation for all men is 2.8. So let's find the standard deviation for all these samples of size 13. Because we're in that central limit theorem. So 2.8 divided by the square root of 13. I'm getting 0.777 if I round. So it's about 0.777. And I want to know what's the probability that the average height of U.S. men is more than 79 inches. More than 10 inches taller than average. And if that's the standard deviation, definitely going to be a low number. So let's go throw that into the David Lane applet here. So when I did that, I don't see any, let me get a pointer. I don't see any, for number 1, 79 is way up off, way more than 3 standard deviations above the mean. And we know that that's just got 0.15% above it. So 79 would be practically nothing. And that's what the calculator shows us. 0% chance that we're going to get a sample of 13 U.S. men and have their average height be 79 inches if that's the true average height for men. Okay? So then part B says 13 U.S. men again, so n equals 13 again. And what's the probability that their mean weight would be 228 pounds or more? Well, the mean weight for U.S. men is 190 pounds, 191 pounds. And their standard deviation is 28, but we want to worry about these samples. So 28 divided by the square root of 13, and what is that? 28 divided by the square root of 13. I see. 7.77 versus 0.77 for the other one, right? And that makes sense because this is 10 times the size. But let's go use that David Lane applet and figure this out, because what I'm really doing is I'm said if the mean weight's 191, how likely is it to have a group of 13 men with their mean weight being more than 228? So we're looking for that area. And again, we can see 228 is, well, they aren't giving us the third standard deviation, are they? But we know it's only 7.7, so what is that, about 213? And 228 is way above that, so we would expect a very small probability of that happening. So sure enough, the height and the weight is way off the chart for regular U.S. men. Now for the NBA players, again, n is 13. And what's the probability that the mean height for NBA players will be 79 or higher? Well, let's do a little sketch. Well, first off, we know the average for NBA players is also 79. Do you see that it's going to be 50% or 0.5? But we'll do the workout. But I'm hoping you see intuitively that's what it is. So the sample standard deviation for 13 men, 13 NBA players is going to be 2.1 divided by the square root of 13. So 2.1 divided by the square root of 13 is 0.58. And we're looking for, now let's do this. 79 is the mean, and we're looking for 79 or more. So do you see that that should be 0.5? Because the mean is the median. That hasn't changed. So we know the answer is going to be 0.5. So let me just pull up that David Lane applet that I've already got pre-filled in, and you'll see that we're right. We really don't even need to do that for this one. And you see, yeah, sure enough, the mean, half of it's shaded in, 50%. Okay, so that wasn't a surprise thing. So then for the mean weight, again, n's 13. The mean weight for NBA players is 221. The standard deviation for these 13, for selecting samples of 13 men, would be, let's see, what is the standard deviation? 25. I'm not sure why I wrote 12. So that standard deviation would be, and why did I write 22? This is Saturday morning when I'm recording this, so I guess I'm okay saying that, making mistakes. 25 divided by the square root of 13, I'm getting a standard deviation for these samples of 6.93-ish. I don't remember what I used in the applet, but we'll do that. So now we're looking for what's the probability. Notice it's still 28, or 228. So their mean is 221. We want to see what's the probability of getting 13 men with an average rate of, or 13 NBA players with an average weight of more than 228. So let's go use that David Lane applet. So in this situation, yeah, I got the 221 as the average. There's the standard deviation, and above 228, so about 15.6 15.6% of NBA players will weigh more than 228. If we compare that to all men, there was 0% of men would weigh that much. So it looks to me, looking at the weight and looking at the height differences, and we know that there's some statistical differences going on here, we could say that the roster of LA Lakers seem to be unusually big and tall compared to U.S. men. Okay? Because the U.S. men didn't have any men that were up that high. A chance of getting a sample of 13 men and having an average height or weight that high was 0. And we're getting some of the NBA players are that big. So, or the chance of getting a sample of 13 NBA players that big, it isn't 0. It's bigger than that. So yeah, they seem to be different. So go ahead and go try those open math exercises now. You'll want to remember to do this calculation for a lot of it. You got to pay attention. If they say a single person, you don't do it. If they say an average of a group of people, then you know you got to do this. You got to do, so let me point it out again. To do that standard deviation for a sample, you're going to take the standard deviation for the population divided by the square root of n. N's the sample size. Okay? So hopefully that'll help. Give me a yell if you need some help and you want to know some online help.